Hey y'all, and welcome back to Coding with Minmer. On today's agenda, we're going to tackle LeetCode problem 791, custom sort string. After that, we'll go over an actual variant of the original question that Meta asks, as well as a follow-up question they might throw your way. Alright, let's read the problem statement. Okay, so we're given two strings called order and s. As you can see, here they are. We're told that all the characters in order are unique, and we're sorted in some custom order. So taking a quick look here, we do notice that all the letters are distinct. There are no extra Z's, O's, P's, or duplicate Y's. Furthermore, this order string is sorted in some custom order, meaning all the letters are jumbled up. They're not in a sensical alphabet that would start with A, B, C, D, E, and so forth. What is our task? Well, this whole block of text describes it. It's a bit confusing, but all it's saying is we want to return a resulting string that has all of these letters in S in the order of Z first, and then O, P, and then lastly Y. Therefore, if the order we're given tells us that all the Z's from the string S should go first, then let's see how many Z's we have. Scanning the string left to right, we only have the one Z. Let's go ahead and push it to our resulting string. Next up, we have an O. Let's do the same thing and loop through to see how many of these letters we have. No, this is a P. Still no. Yes, yes, and yes. No, and no. Okay, not sure if that was coherent, but we had found 3 O's. Let's add them. 1, 2, and 3. After that, do we have any P's in our string? Yes, we do. We have the 3. Let's append them to the end of our result. 1, 2, 3. And at last, we have a Y. Let's do the usual and iterate left to right in search of any Y's. Turns out we have none, thus we have no Y's to add. This is a thing that can happen where we're given characters in the order parameter that may not exist in our string S. On this note, you may be wondering, can the opposite situation occur, where we have characters in the string, say A, B, B, that aren't in our order? Yep. If you take a look at LeetCode's first example here, there's a D that doesn't exist in the custom order. And we observe that the D is simply appended to the very end of the resulting string. And though the problem description doesn't explicitly state it, the rule is if there exist letters not in our order, then they can be put anywhere in the resulting string. So for example, we can put it like this. Or we can have the A first and then the 2 B's at the end. It doesn't matter. For us though, we'll copy LeetCode and put all the leftover letters at the very end. So here, A, B, B would be pushed like so. This is our answer, and that's what we'll return in our function. But we must remember who we are. We are software developers. How do we translate this logic into code? Well, little did we know, we already kind of did that. Unknowingly, we suggested an outer for loop through our order parameter, and for each one of those letters, we ran an inner for loop left to right through our string, and whenever we found a matching character, we'd push it to our resulting string. The time complexity of this solution is terrible though. It's big O of S times O, where O is the length of order, and S is the length of our string S. And not to mention, there's additional complexity with the excess characters in our string as well. How do we optimize this? Well, let's reinspect our naive solution and observe why the performance was so slow. In the outer for loop, we started with Z in our order, so what did we do? We parsed through every single letter to find Z's, which meant we looped over letters we also didn't need, namely the P's, O's, and the A and 2 B's. We added the singular Z and then committed the same crime when we tried to find how many O's we had in our string. Sure, we found the 3 and we're grateful, but we also redundantly went over the P's again, A and 2 B's, as well as the Z. We're noticing a pattern here. We're going over our entire string for every character in our order parameter. We'd rather pre-compute our string in such a way to make the lookup from any letter from order a lot faster. Okay, so let's examine our string. For the letter P, we just needed to know that there was a grand total of 3 P's. For the O's, it was also 3, Z is 1, A is 1, and B is 2. Therefore, at the beginning of our function, why not loop through our string one time and one time only, and not for every single letter in order, and keep track of each letter's frequency? We can insert it into a hash map where the key is the letter and the value is the frequency. Seems appropriate to me. The next step seems pretty clear now. We should loop over our order, and for each character, take this Z here, we can now look up in big O of 1 time complexity to know how many Z's we had found. We look it up by the key and realize there was only the 1. Therefore, we can add that to our resulting string. I already added it from the naive solution before, so this time let's just checkmark it to say that we added it. Okay, we move on to O. We look it up in our map very conveniently to see that there are 3 O's. Fantastic, we have the O's covered. Next up, we have a P, in which case we also have 3 P's. Let's add those. And lastly, we have Y. Our map, though, tells us that Y does not exist in our string to begin with, and that's correct. We never added Y to our result. Okay, so we exhausted every letter and we're done. Or are we? We still need to tack on the leftover letters, the A and 2 B's, at the end of our result. It's obvious we have to do another for loop for these leftover characters, but where can we loop? Well, we only have 2 choices. It's either our string S, where we have ABB, or our hash map that also has A and BB. Well, I refuse to touch the S string again since it'll chuck us back into terribly slow time complexity land, so why not the map? Let's do that. Okay, so we're looping, and looping until we realize we have no idea which letters are leftover letters. How do we distinguish letters we already push with letters that are leftovers and thus haven't yet been added? Sadly, we can't tell. We stare blankly at a wall for hours on end until we realize when we had looped through our order parameter from before and added the frequency of the letter to our result that we had used up those letters, right? We used up the 3 P's and added to our result, the 3 O's and added that to our result, 1 Z. You get the idea. We no longer needed them. So can't we just erase them from our map? That way, when we do have a for loop to add all the leftovers, the only letters we'd encounter are the ones that were in our original string, but not in our order parameter. Perfect, so we loop through, we encounter an A that's happened 1 time, amazing, we add that. And then lastly, we encounter B that's happened 2 times, let's add that as well. And with that said, we have our full result and we did it in a faster way. We did have so many loops though, so what's our exact time complexity? Our first loop went through S to create our map, remember? Therefore, so far we have big O of S. Our second for loop went over the order parameter to add the frequency of letters to our result. But wait 1 second, I can't believe it took me this long to notice that the length of order is limited to 26 letters, or in other words, the English alphabet. And as it turns out, our S string can only have lowercase English letters as well. But anyway, if the upper bound length that order can ever have is 26, then we can generalize the big O of O to 26, which is a constant, and since it's a constant number that never changes, we don't count it towards our overall performance. Okay, moving on. Don't forget we had our third and final loop, which went over our hash map to add any leftovers to our result. But since the string that we built this hash map from can only have lowercase English letters, then the maximum number of key value pairs this map can take on is 26. We know what to do with these constant time complexities. We can trash it entirely. And with that, we arrived at our generalized time complexity of big OS, where S is the length of our string. The space complexity is big O of 26. Because of our map, it can only take on 26 key value pairs. Therefore, it's arguable that we have constant space for our solution. Great. The code now should be trivial. Let's get started. Okay, so what was our data structure of choice? It was a hash map that had a key of the letter and an integer for the frequency. Let's call it freaks for frequency. Now for the bulk of the logic, we had 3 for loops, remember. The first one looped through every single character in our S string. We kept track of their frequencies and increased it whenever we encountered that particular letter. And now that that's pre-computed, we can loop over our order parameter and add all the letters that we found into a result. This is what will ultimately return, so let's do that before I forget. Let's add each character in the right order this many times. And once we've done that, we've used it up, right? We're going to erase that letter from our map. Amazing, now we need our third and final loop to add all the leftover letters to our result. Remember, to do that, we iterated over the key and value of our map. We're confident we're only going to encounter the leftover characters, in which case we'll add them in the same way. The first parameter is the frequency, and the second one the character. Okay, awesome. Let's get into the first variant. Luckily, Meta spares us a headache and doesn't ask too tough of a variant. If you know the original LeetCode problem by heart, you may do a double take for a split second. Rereading the entire problem description, I'll tell you right now that the only thing that changed is how we're given the order parameter. It's now a vector of characters, no longer a string of characters. We realize both are pretty much sequence containers, and recall from the OG problem, the only functionality we needed from the order parameter was to loop over it. And since we can totally do that in a sequential way with either data structure, absolutely nothing in our code changes. Before we dive into the code, where I flash you the same implementation for a few seconds, just note that Meta may not give you defined parameters. You may have to come up with it yourself. Either that's a string or a vector, it doesn't matter, just go with what your gut tells you. Alright, let's see the code. Okay, welcome to the shortest variant alive. The only thing that's changed is in this method signature, where order is now a vector of characters. The only thing we do with order is loop over it on line 9, and as you can see, a for range loop works the same for a string as it does for a vector. Okay, that is it. Let's get into the follow-up. Alright, so we've solved the original LeetCode problem as well as a variant that was barely different. We're sitting real nice until the interviewer asks you a follow-up question. Take a look here. Can you optimize your solution? That sounds vague, and that's because it is. In an interview setting, that's about all the hints you'd get. I'll tell you right now, we can't do any better than big OS from before, where S is the length of our string. But if we take a sneak peek at one of Meta's secret formulas, we're mind blown and learn that the frequency hash map data structure that we opted for in the original LeetCode problem was a poor choice. Among other reasons, a map can suffer from collisions, which can really slow down our performance. If you disagree with me, don't at me, take it up with the people at Meta. Instead, what they're looking for you to utilize is a vector to store all the character frequencies instead. Let's take a look at an example, swap out our data structure, and see what logic has to change. Okay, so as you can see, here are our parameters, S and order. Now, instead of a hash data structure, we'll initialize our vector for the frequencies. Let's name it freaks, just like we did before. Just for some context of how to initialize the vector, recall from the OG problem, I called out this constraint, where all the characters we can be given consist of lowercase English letters only, which is a size of 26 from A to Z. Therefore, I'll allocate 26 slots in our frequency vector up front. As we can see, we now have one element for each letter. And to make it work, we can be clever and map each lowercase English letter to an index. So A would map to index 0, B to 1, C to 2, D to 3. You kind of get the idea, so let's skip to the later elements, where Y is mapped to index 24, and lastly, Z to index 25. And yes, it's 25, not 26, because we're working with indices, it's off by 1. Anyway, all their respective values will be defaulted to a frequency of 0. That part makes sense. But the question I have is, how exactly do we map a particular letter to its designated index? I ask this because when we go through our first for loop over each character in S, we'd like a system in place to, for example, convert this B to its index of 1 so we can increment its frequency to however many times we've seen it. Well, this is where ASCII comes into play. Computers fundamentally work with numeric values, so when it sees a symbol like A, for example, it actually sees a decimal 97. For B, that would be 98, C, 99, D, 100. Skip a few because this is redundant. Y is 121 and Z is 122. This may seem arbitrary, but this unique mapping is universally agreed upon and is known as the American Standard Code Information Interchange, or in other words, ASCII. Okay, so let's take this B again in our for loop, whose value we know now is 98. What can we minus from it to get an index of 1? Well, we look around awkwardly until we realize that the symbol A has an underlying decimal value of 97. From pure observation, we can subtract the 2 and get exactly what we want, index 1. Okay, so with that, we can happily increment the frequency to the 1. Let's move on. In our for loop, we next encounter an A. We can do the same thing, minus 97 from an A of 97 to get index 0. That's perfect. We increment the count of A to 1. We've seen it 1 time so far. Next up, we have a B. We do the same maths, remember, to get index 1, so that we can now increment our frequency count to the 2. We move on to C, whose decimal value is 99. We'll normalize it so it can fit in our vector of 26 elements. Minusing the 2, what do we get? We get index 2. So let's increment the value there to 1. On the last iteration, we have a Z. What's 122 minus 97? Well, spoiler alert, it's the 25. It works out. Let's increment that count to 1. Great, we got over the biggest knowledge hump for the follow-up. Now we can continue our same workflow from the original LeetCode problem. Now that we have our frequency vector, we can iterate through our order parameter, the second for loop, remember, and do the same subtraction math and add the frequency of characters to a resulting string called result. Okay, so on the first iteration, we have a C whose decimal value is 99. We can minus A from it, or in other words, 97, to get an index of 2, which makes us realize we had a total of 1 C. You can verify that in the original string. Here it is. Great, so let's add that to our result. Recall in the OG problem, we erased the entry in a map when we used up the letter. Here, however, we have a vector. So alternatively, we can just overwrite the frequency to 0 to say that we've used up all of the C's. There's nothing left. Great, let's move on in our for loop. We have a B next, which I'll spare you the math. We have 2 B's, and it's true. Here they are. Let's add them to our result. Last thing we'll do is overwrite the frequency with 0. We used up all the B's. Moving on to the last iteration, we have an A. We can look that up in our frequency vector to see that we have 1 A. Let's add that to our result like so, and reset the frequency to 0. All right, but remember, we're not done yet. We have to go through our last for loop where we try to add any leftover characters in the S string that wasn't in the order string. And eyeing it, it's obviously the Z. What we'll do is iterate through our vector, and if the frequency is not 0, then it must mean it's a leftover, and we should append it to the end of our string. Okay, so on the first iteration, we have an A, but we have none of it, so we simply move on. We don't have any B's either. We move on. No C's. And no D's. We keep going until we encounter index 24, which is a Y. We have none of that. So we move on to the last element where we have a leftover Z because the frequency is non-zero, it's 1. Let's append that to our result. But hold on, how do we map the index of 25 to a character of Z? So far, we only did it the other way around from character to index. Let's not overthink it. All we have to do is the inverse. We can instead add 97 to the index of 25 to get 122, or in other words, z. Fantastic, we can add the z like so. This is our ultimate result, and that's what we'll return. The time complexity is big OS, and the space complexity is big O of 26 because our vector is fixed. It can only have the allocated 26 elements, which really is just constant space. Okay, let's go into the code and see what changes. Okay, so first things first, we no longer want our map. We'd rather have a vector of ints of the frequencies. Remember how we initialized it? We allocated upfront 26 elements whose frequencies were defaulted to 0. Our first for loop will remain the same, but to map from character to index, we minus the letter A, remember, which in decimal form is 97. In our second for loop, the logic changes ever so slightly. We must remember to minus A, and the way we denote that we used up the frequencies is different in a vector than a map. Instead of erasing it by the key, we simply set the value that's there to 0. We used up all those letters. Now for the last for loop, we actually need a loop with I so that we have access to the indices of our frequency vector. And if we have that, then we have to access the frequency by I. And then remember the last bit of math, we added to I the index of A to map from index to character. And that is it. ASCII is another tidbit of info that Meta wants candidates to know, but with this, I hope it made more sense. All right, good luck on your interviews. And if you learned something today, please make sure you like, comment, and subscribe. Thanks for watching.